In Lesson 5, we looked at voltaic cells, how to construct voltaic cells, and the shorthand diagram of voltaic cells. Today we're going to look at the voltmeter of the voltaic cells that we constructed in Lesson 5. They're known as the potential difference of a cell. We're going to calculate the electrode potentials in this case for Lesson 6. From last time, Lesson 5, constructing the voltaic cells involve 5 steps. First step, to submerge the metal strip in their solution of its ions. You then look at the electrode potentials by looking at the metal strip's interaction with the ions in the solution, and you're able to figure out the equilibrium. So does it lie further to the product or further to on the reactant side through the half reaction equations, and you then attach the two solutions and the metal strips with a circuit. The voltmeter will then tell us the cell potential difference, and we would have to add a salt bridge in between these two beakers in order to balance and displace the potential difference so that the circuit keeps going. Today we're going to look at 9.2 and go into 19.1, which is energy conversions of the higher level IB Chem Major topic. How are electrode potentials measured? Recall, electrode potentials are talking about the metal, right, submerged in the ion of its solution, and the interaction of that metal with the ions in its solution. Here are a few units to take a look at. Electric current in amps, electric charge in coulombs. Faraday's constant is going to be used to calculate Gibbs Free Energy. Potential difference is in volts. Usually when we connect two different half cells together with a circuit, that's called a cell potential. The amount of energy is in joules. The electromotive force is the greatest cell potential difference. So you can call it cell potential difference, or you can call it EMF. And also remember that cells in series have the same current flow through all components because they're in the same path. Cell potential is denoted as E subscript cell. That value is the plus 1.10 volts value on the voltmeter when you attach a circuit between two half cells. This specific circuit we looked at all of lesson 5, and that's the zinc and copper reaction. But what does the 1.1 volts mean? The fact that it's positive, does that make a difference? So we're going to take a look at how this value came about. This value came about from standard hydrogen electrode. So we obviously, electrode potential by itself cannot be measured unless it's linked to another cell. So we can't measure electrode potentials unless we connect two half cells together with a circuit. Because of that, we can't just connect two different metals all the time. Then we don't have a benchmark to set it as, right? So we use a hydrogen electrode. Standard hydrogen electrodes hold 0 volts for the electrode potential. And so because of that, it's really easy. You can just connect the hydrogen with any metal, any non-metal you want to figure out their electrode potential for, attach a circuit with the half cells, and you'll be able to determine the electrode potential of that metal or non-metal. This is how a hydrogen electrode looks like, and this hydrogen electrode could be used as an oxidation half reaction or a reduction half reaction, right? Because all of these reactions have two-way arrows, so they form equilibrium depending on whichever metal or non-metal the other half cell is. So with this hydrogen electrode, the half reaction equation is just 2 hydrogen plus 2 electrons yields hydrogen gas, H2. standard electrode potentials, E theta, when hydrogen is placed in another half cell with copper, so we want to figure out the copper's standard electrode potential, then what we would do is connect the circuit, and we see that it's a plus 0.34 volts. The positive value means that it has a greater tendency for Cu to be reduced than hydrogen. So it means that's why copper is the cathode on the right of the cell, and that's why the cathode is reduced. You can think of it as, remember the zinc and the copper reaction from lesson 5? Remember how the copper metal strip had a more positive electrode potential. So reduction and cathode, cathodes and reduction, usually the metal strip hold more positive charge. So because they're more positive, that means the electrode potential must be more positive. That's why it's a positive value. Let's take a look at the zinc. So when we want to figure out the zinc value, zinc placed in a half reaction with hydrogen, instead of the previous one where hydrogen was the oxidation half reaction, this one, hydrogen is being reduced. So hydrogen being reduced, hydrogen is in the cathode, and that's why zinc is on the left-hand side and zinc is the anode. You can see that through this reaction, the potential difference, standard electrode potential here is negative 0.76 for zinc. So because it's more negative, it tells us, remember zinc, the metal strip from lesson 5 was more negative, right? It means that it's more oxidized because there are more electrons that are kind of deposited at the surface, and that's usually indicative of the anode, indicative of the half reaction being oxidized. All of the half reaction standard electrode potentials in volts can be found in your IB Data Booklet, Table 24. So take a look at Table 24. All the ones that you need to know are on there. The purpose of a standard potential difference of a cell, 3 things. We can calculate the cell potential. That's denoted by standard is the theta, right? And cell potential is the E cell. We can determine spontaneity of the reaction, and we can also compare relative oxidizing and reducing power of half cells. We're going to start by calculating the cell potential. Calculating cell potentials, they follow a very simple equation, and the equation is the cell potential, standard cell potential, equals the standard electrode potential of the half cell, that's reduction, so at the cathode minus the anode. Anode is where the oxidation occurs. So in the zinc and copper half cells, how about you look at data table 24 in your IB Data Booklet. Look at the standard electrode potentials of copper and zinc, or just a couple slides ago we talked about the standard electrode potentials of copper and zinc, and calculate the cell potential. The next thing we're going to look at is determining the spontaneity of the reaction. Spontaneity, as you guys should remember from last year, we looked at Gibbs Free Energy, right? Do you guys remember if when Gibbs Free Energy, delta G, is negative, is that non-spontaneous or is that spontaneous? So, yes. You guys hopefully got to the point that delta G, when it's negative, means that it is more spontaneous. So let's see how delta G is related to the standard cell potential. The voltaic cell will always run in the direction that gives a positive standard cell potential. Okay, it has to be positive. This is for voltaic cells only. And that's because a positive value tells us that it is spontaneous. The only reason why a positive value tells us it's spontaneous, you're going to be like, well, you just told me that Gibbs free energy, delta G, when it's negative, it's spontaneous. So how can this be positive and be spontaneous? That's kind of counterintuitive. That's because when you look at the Gibbs free with respect to the cell potential, it's in this equation. So do you see how Gibbs free by itself, on the right-hand side, it consists of the number of moles of reactants involved, Faraday's constant, and the cell potential. And all of that is multiplied by a negative value. So therefore, the more positive the cell potential is, the more positive the reaction is more energetically favorable. And because it's more energetically favorable, the more positive it is, it means that the more negative the whole right portion of that equation is going to be. And the more negative it is, obviously tells us that it is more spontaneous. So now we see how the cell potential is related to Gibbs free energy. So now let's come back to this slide and figure out this question. So how do you use the values to determine whether the reaction will occur spontaneously under standard conditions? Here is a reaction between nickel and manganate ion. So step one, we figure out that nickel is the one being oxidized and the manganese is the one being reduced. We then find these two half reaction equations on table 24 of the data booklet, and the nickel half reaction gives us a negative 0.26 volts, and the manganese 2 plus gives us a negative 1.18 volts. We use the equation of the cathode electrode potential minus the anode positive electrode potential, so negative 1.18 subtract negative 0.26, that gives us negative 0.93, and that's the standard potential of the entire cell. The fact that this is negative tells us that this reaction in this form is going to be non-spontaneous, right? So in order to be spontaneous, actually, what's going to happen is that this whole reaction is going to be flopped. So in order for it to be a spontaneous reaction, it should be nickel 2 plus manganese solid becomes the nickel solid and the manganese 2 plus. So now let's have you guys calculate this next question. Calculating the standard free energy change. Remember, that is what? Gibbs free energy. So put all the information that you have together to calculate the delta G. Lastly, we're going to look at comparing relative oxidizing and reducing power of half cells. So recall previously again, data booklet, table 24. We have a list of all the standard electrode potentials. What we need to remember is that the electrode potentials goes from more positive electrode potentials all the way to negative. So when the electrode potentials are positive, recall positive means it becomes reduced more often, so it's in the cathode more often, right? Because the metal strip is more positive. So the positive increases in oxidizing agent strength. And the reducing agents increase as you go down. So as it becomes more negative, it increases in the strength of the reducing agent, which means it's becoming oxidized a lot easier going down. Now let's try this next question. So a quick final recap. Electrons always flow towards half cell with highest electrode potential value. Higher the E theta, standard electrode potential, the stronger the oxidizing agent. So remember, the more positive. The lower the electrode, standard electrode potential, the stronger the reducing agent. So the more easily oxidized. Standard electric potential give us the energy feasibility of a reaction, and it's not the rate. So it doesn't give us the rate. So more positive of a standard electrode potential means it's more spontaneous, but it doesn't tell us anything about the rate. Standard electrode potential is in standard conditions, so any of these factors could affect the spontaneity of the reaction. And here are the equations to calculating the Gibbs free energy and